All right, so welcome to part 5 of the course. This is the final segment of the course, and it is going to be on magnetic forces and electromagnetism, which basically ties everything together. You will see a lot of the ingredients actually being tied together in the beginning of from the beginning of the course, including free body diagrams, including the concepts of fields, of electric fields. We're going to put them together with magnetic fields as well. So today we're going to focus on magnetic forces and magnetic fields. And a lot of the problem solving techniques will be very helpful in terms of, hopefully these are just general skills that you learn throughout the course that will help you in any physics course, and also hopefully beyond the physics courses as well, such as understanding definitions whenever you learn something new, always asking why, try to ask as much questions as why do things happen, and try to dig deeper in general as much as possible whenever you learn something new, and also ask why do you care about something, because that is what makes the topic interesting, and also to give you a reason to live, to learn this stuff. Yeah, all these are very useful. So today we are going to address magnetic forces, and it is a whole new concept as well. And so we will going to address some of those questions, such as what is it, and what does it do, and why do we care about it? Right, so for example, just a quick recap with capacitors, immediately the first question when you learn something, that if you've never heard of what a capacitor is before, hopefully the first sentence, what is it? Basically that translates to, can you explain it in simple words to a 5-year-old or to an 8-year-old? I think that's a good litmus test of do you know what you're doing? So that is very simple. It's a device that stores charges, and then you go and dig into what does it do, which is all the technical stuff, all the formulas and stuff, and then also remember the applications of why do you care about it, right? It gives you direction for where you're going with this. All right, so magnetic forces is the new concept today. We basically, I think this is an interesting topic. To me, it's also one of the most interesting forces of all. First of all, it might be interesting to you because it's something that is not as foreign at first when it sounds, because we all played with magnets as a kid. But when we dig a little bit deeper and look at how the forces actually act, it's one of the weirdest forces that I know. It's the only force that the influence, whatever the source is creating an influence on an object, the object does not react directly to the influence. It reacts perpendicularly to it. So if there's a magnetic influence pushing something this way on another charge like this, it actually creates a force that acts perpendicular to it, which is very weird. And we'll see why today. Well, we'll investigate it a little bit more today. And at the end, we will be able to see some applications as well, which is very important. Namely, the first one, there's a teaser ahead. Hopefully I'll get to it because there's a lot to cover today. One of the main application is motors, electric motors, in particular called direct current motors or DC motors. And this is what makes cars possible, or more specifically, electric cars. So actually in part 2 in thermal physics, we learned about how do gas-propelled cars work with internal combustion engine. It's basically a heat engine. You basically have gas cylinders that expands and contracts in a cycle, in a thermal cycle, a thermodynamic cycle, and then you can create things. But in principle, you don't need any electricity for that to happen, for a gas-propelled car to happen. But now we'll see, if you want an electric car, which brings us into the modern age of actually any electricity device, how do we actually create work done from this? It's all thanks to having the magnetic force. Okay, so with that motivation, we will start by reminding you how it's obviously a non-contact force, and how do these work. And the basic principle is the same. Sorry, something's keep popping up as well. Let me just get rid of that. Computer. Okay, cool, sorry. Yeah, all right, so you've probably played with magnets, so you know, for example, if you have two north poles like this, and they will try to repel each other, just like two positive charges try to repel each other. And how do we actually analyze this in physics? So the whole of week 3 and week 4, we introduced a new concept, is trying to answer that question. How do non-contact forces work? So you first treat something as a source, and then the other object of interest, we call it a test object, right? And how does the source actually influence the test? It's not by some magic influence. It's by something very concretely or mathematically well-defined, even though it's very abstract to think about. But it's very concretely mathematically defined, is that the source is emitting some sort of field, and the test charge feels that field. So there's no sort of spooky action at a distance, kind of. This is a term coined by Einstein, although he was referring to something else. But it's not this guy mysteriously sort of sees this guy from at a whole distance of vacuum, but this guy actually creates something that's invisible, called a field, and this guy experienced that field. Yeah, so although you don't see this with your naked eye, it doesn't mean it doesn't exist. Just like, you know, air. You don't see air, but it doesn't mean that it doesn't exist, right? So don't be fooled by the fact that you can't see it. It doesn't exist, because it's very real in that sense, in creating effects on something else, right? So to quantify this, this should be looked at in 2 steps. So whenever you try to analyze non-contact forces, from now on, you split it into 2 questions. The first question is, how does the source create a field? And the second question is, how does any test object reacts to the field? Okay, so this works for gravity as well. So gravity has the Earth and an apple. The Earth is creating a gravitational field which pulls all the mass towards it. And then this guy will experience the gravitational force, right? Force of gravity. So this 2-step process is the Earth creating this field, and then the field creates a force on the object. Okay, same thing as electric fields, right? So for an electric charge, let's say this is the source, right? So you have the electric field lines like this, and then your test object experiences that field. So we split it into 2 questions. How does the source create the field? And we know that the magnitude is given by this formula, right? And the force that this guy experienced is given by this formula, right? So this is the test charge, and it sits in an external field, so that is created by the source. So this is the source creating that field, and this is the test charge feeling that force. Okay, so we'll split today in first addressing how do things create, things meaning sources, create a magnetic field, and step 2 is how do things react to a magnetic field? And this time the things is objects of interest, which we call test objects. Reacts to the magnetic field. Okay, and then finally we'll also talk about applications. Okay. So first of all, the symbol we use for magnetic field, right? For electric field, we use E. And for gravitational field, there isn't really a agreed symbol. You can use G, you can use capital G, little g, whatever, or I, sometimes that happens. But for magnetic field, there is a agreed symbol, and it's B. Okay. So technically, it's a vector quantity, but if you just write B, that means it's the magnitude of the magnetic field, vector, magnitude of B. So this is just a lazy way of writing this. And a lot of times, as we learn, we can actually disentangle and analyze the magnitude and the direction separately. However, in this chapter, actually, we will work with the vector quantity a little bit more, because it's actually quite difficult to just work with the magnitude in here. So that's why this is the last segment, last chapter, or the last part of the course, because we want to get familiar with all the basics first, and now we're actually putting all the things together, including ability to work with vectors. Okay, we'll talk more about that. Don't ask me why it's B. I have no idea. We're just running out of letters, right? M is probably used for mass or something, or something else. So we're running out of letters, so everyone agreed on B. All right. Okay, so the first thing is, also, just right off the bat, I'll just for you to know where we're heading with this is, we'll go, and there are 4 key formulas that we're going to explain today, that we're going to address. So I'll just state them right up front, and then we'll go through and handle them one by one. One is the magnetic field strength remember, magnetic field strength means the magnitude of the field vector, is given by this, if it is created by a wire. So we'll go and address what each of the symbol means as we go, but I just want to state the different formulas. The second one is if it's by a solenoid, or I should say infinite solenoid, it's given by this formula. Or an easier version, you can write it as this. So these 2 are dealing with the first question of how do things create, or how do sources create a magnetic field. If you have current, basically we'll learn that will create a magnetic field. So this is just like the the formulas that you learned. For example, for a point source, this is the formula that creates the electric field strength, or if it's a plane, if it's an infinite plane, that's the formula. If it's an infinite wire, then that is the formula, right? 2 pi r, and then there's the epsilon as well, like that. Okay, so these serves as answer to question number 1. And then now the question is, how do things react to it? How do things react to it is, we'll see this formula. And this time we actually need vectors for it, as we'll see, because of a very special nature about magnetic forces. And also this one. So we'll address basically the goal of today is to explain these couple of formulas. All right, one thing off the bat I want to address is this little cross over here. And this is very important, all right? This is not a times, this is a cross, okay? So I mean, yeah, it's the same symbol, but we call it a cross. So this is called a cross product. So if you haven't seen this before, we'll explain this a little bit in this course, but you might want to watch some YouTube video and brush up on what's a cross product. And so right off the first slide, I want to warn you that for vectors, what can you do with vectors? If you have two vectors A and B, you can add them, you can subtract them. But remember, vectors are basically arrows, okay? So what does adding arrows mean? It's just you combine them with head to tail. What does subtracting arrow means? That looks a little bit weird, but that just means adding a negative of the arrow. So what does a negative of an arrow mean? It's just, if that is B, then negative B is just you flip the direction. And now, if you take A and add negative B, it's just basically saying, instead of adding it like this, you add the 1 to the negative B, right? So this is the result of A minus B, and this is the result of A plus B, A vector plus B vector. This is the result of A minus B, like that. You basically take A and add to a negative B. Now, if you remember, vectors is just a fancy word for arrows. So what does it mean by multiplying a vector A and multiplying with B? There's no such thing as taking two vectors and multiplying together. That's why it is such a bad idea. You'll never see any textbook just put two vectors like this together, okay? This means nothing, okay? In fact, maybe more specifically, there's two ways to multiply vectors. Multiply, let me put that in quotes, right? There is, or I should say product, there's the dot product. So you should specify A dot B, or the cross product, A cross B. Okay. So if forgive me if you've learned this before, if you already are familiar with this, just bear with this in case this might be a little bit more foreign to some of you. And if this is completely new to you, unfortunately, you do need to do some reading, a little bit of maybe just 10, 15 minutes of just Google it and YouTube some good video explanation of that to supplement your understanding. We will go through a little bit, but it'll definitely help if you have some understand the math a little bit more than what I can afford to explain today. Right? So there is two types of products when it comes to vectors. So never write just like this. You must specify whether it's a dot or a cross. If you don't specify it, it doesn't make any sense. There's no such thing as the dot product is more popular than the cross product. Like if you don't, there's no default. They're equally relevant in mathematics and in physics, right? They're equally prevalent in, it depends on what context you do, they're both relevant. And in this course, cross product is probably the archetypical, it's probably the archetypical applications of cross products in magnetism, okay? So just a quick warning about this notation, make sure if you write with vectors, you must have either a cross or a dot. And in this case, it has to be a cross product, okay? All right, so let's do the first question, right? The first question is, I'll just put this into little parts. It is sources of magnetic fields. So what causes magnetic fields? So since we use B for magnetism, sometimes we'll call this B field, or sometimes I might call it B field. I'll use these words depending on how lazy I am, how much what I want to write. All right, so there are two sources for it. Okay? There are two sources for magnetic fields. One is permanent magnets. And two is currents. And this might be surprising to you, unless you've learned some of this before. If you haven't learned this before, okay, magnets, that's probably what you expect, right? But you probably, if you haven't learned this before, you'll be surprised that currents also create magnetic fields. So how does this work? Let's start with magnets, okay? So actually, let me put a little star here, because what I probably won't be able to get it today, but maybe next lecture we'll readdress the fact that actually permanent magnets are a lie. Permanent magnets are actually just currents. So technically, there's just one source of magnetic fields. However, let's start with assuming there there's two, so it's more close to our daily life experience. But then you realize all magnets are basically just currents by the end of maybe next lecture, right? So that's a little caveat there, a little footnote. Yeah, and also while I'm at it, let me state the SI base unit for magnetic field as well. The SI base unit is Tesla. Okay, so symbol by T, right? So something like 1 Tesla is actually a pretty strong field. Yeah, depending on the context as well. Okay, and I know what you're thinking. This is not the car. this is named after the scientist Nikola Tesla, which is probably one of the most underrated scientists in the 20th century, in my opinion. And next lecture we'll actually talk more about this guy, and in particular how he had great ideas in uniting magnetic fields and electric fields. One of the greatest inventor and scientists in the 20th century that is largely ignored by people. Okay, sorry, let me turn my Wi-Fi off. That's this. Okay. All right, so let's talk about basic properties of magnets. So this is going to be brief. You can read up a little bit more in the textbook because it's mostly very intuitive. First of all, there is 2 types of poles. So we call them poles, which is North Pole and South Pole. And the basic idea is North and North would repel, South and South would repel, and North and South would attract. Okay, so I'm not going to go in any more depth than stating this as just a fact. All right. And so it's very similar to electric charges, where like charges repel, opposite charges, in this case, we just use a different word, we call them poles. Property B, is a little bit more unique. So this part looks like electricity. The second part it's completely different from electricity, is that there's no monopoles. How many of you know what a monopole is? So a monopole, as it suggests, mono means 1. So in this world, it doesn't actually exist any poles. You cannot have a North Pole on its own. It always comes with a South Pole. So whenever you have a permanent magnet like this, North and South like this, if you cut this in half, you don't get a North Pole and a South Pole, right? Even if you chop this in half like this, what you get is you get 2 magnets like this. Right? Maybe I can bring up a picture. And so basic property of it. And even no matter how you chop this up, you'll always get a North Pole and a South Pole pair like this. So this is a very interesting fact. And maybe by the next lecture, I will actually be able to explain why this happens. However, what's interesting is I can only explain why this happens in the context that we know about theoretical physics up to this stage. And people have been studying this theoretical physicists have been studying this for ages. And there's nothing in the laws of physics that actually forbids one to actually create just a single pole, although they just for some reason, we don't find them in the universe. This is another big mystery in physics. This reminds me of a story I used to do tutoring to a kid, and one of the kids actually one day asked me, so what do physicists actually do research on? Aren't everything already figured out? So that sounded so funny to me. That it gives the illusion to that when we teach all balls rolling down slopes, it seems like everything is 17th century physics. It's all figured out. But there's so many deeper questions in the field that we still struggle with, and you probably never thought people would even ask these questions. But yeah, monopoles is a big mystery because there's nothing forbidding them to exist. In fact, all the equations say they could, and there's no reason they shouldn't exist. For some reason, we couldn't find them. So either this reveals there's something deep in the laws of physics that we're missing, or it's just one of the weird coincidences, which scientists don't like to think coincidences happen this naturally, unless there's some natural explanation for it. So yeah, if any one of you find a monopole in the future, let me know. We'll write a paper together and go to Sweden and get a Nobel Prize for it. So then the last property is about how the magnetic field works. So the B fields go from north to south. Okay, so if you have one end of the magnet north over here and another end of a magnet like this. So although monopoles don't exist, just imagine there's another side to this, there's another side to this. I'm just drawing the key bit over here. The magnetic fields would go from north to south. So you can think of this almost like a capacitor or electric field and analog, where if you have a positive side and a negative side you will have these uniform fields over there. So how do people know this? How do people even know the magnetic field goes from one side to another side from like that? They first put a magnet, let's say, and put a piece of paper on top of the magnet. So put a magnet underneath the paper, and you can sprinkle a lot of iron filings. If you've never seen this before, some of you might have seen this experiment before, you sprinkle a lot of iron filings on top. So filings are just little thin strands of iron. So they're very light and very, they're iron, so they're metal. And you will see that if you just sprinkle them around and then just tap the paper a little bit, you will see they form this pattern. Okay. So I'm not going to be able to draw it very well, so I'll just show you a picture of it like this. So these are little thin iron filings you can sprinkle around it. So after you sprinkle on it, as they fall on the paper, they'll form these patterns. Even if they don't form it right away, you shake the paper a little bit, so they readjust to actually experiencing that the field that creates by the magnet underneath, and they'll form patterns like this. So you can put little compasses next to them, which is actually just another piece of metal, but this time it's on a needle, so it's easy to swing around. There's very little friction, so that the metal will react to whatever the source is generating. So you'll see the compasses will actually form these arcs, which is basically telling you how the magnetic field shape looks like, right? So we can redraw it in lines like this. Okay. So first of all, outside, you can see we'll try to redraw it like this, and we assign an arrow, even though the iron filings in nature doesn't tell you which way does it always go, from north to south or south to north, right? The arrow doesn't mean anything in nature. When you sprinkle the iron filing, it just follows the pattern. But we need to make a decision when we're doing math. So we just, by convention, decide, all right, just like in electric fields, we decide positive charges positive source charges would emit the electric fields. We'll say the north pole emits the magnetic field. So it goes from north to south, just like it goes from positive to negative. Okay. Any questions about this? So that's all about permanent magnets, really. So you learn sort of this diagram. Inside, I wouldn't actually draw this, it doesn't matter. But since you can't really put a test object inside the magnet realistically, right, you can and have it move around. So I wouldn't necessarily draw it, but it's not a big deal, even if you draw it or not. It doesn't matter. You won't get marked off for that. The important point is the outside. So you can see how this occurs as well. If you put two together, then the south pole is attracting them. If my surface area here is large enough, then it's like the infinite plate or infinite capacitor kind of scenario, then you'll have pretty uniform lines instead of diverging lines like this if you have a large surface area on that side. Okay. All right, so that's all about magnets. Then how about wires or currents? So this is interesting if you didn't know that currents actually create magnetic fields as well, other than just magnets like this. So how do people figure that out? Is they did a very similar experiment. Is you take a wire like this, pass a current through it. So technically you connect that to a battery. I'm not going to draw the rest of the circuit where you connect it to a battery. Now you have the wire go through a paper, punch a hole in the middle. So have it perpendicularly, let's say perpendicular first, just to keep it simple. Go through a wire, and then you sprinkle iron filings around it. And then you see the iron filings actually form little concentric circles. You might hear this word a lot, concentric, which means they share the same center. Concentric circles. So this is a word we use to describe this pattern. Right. So all the circles share the same origin, share the same center. So that means concentric, like this. So you can now put in little compasses around it, just like the magnet case, and then you'll see the compass will follow this direction as well. Right? And I'll show you a picture of that. Right? So you can see if you have a wire, whether you can cover it with some insulating plastic or not, either way, they will go around like this, right? So that suggests that whenever you have a wire, that is producing the same magnetic effect. Well, not the exact same pattern, but it is creating some magnetic effect from just like the permanent magnet. So this is actually the first hint that there's a connection between electricity and magnetism, right? Magnets, before you learn about this, or before you know about this, you might think that magnets is what causes your stickers to stick on your fridge, or these things that, but in principle, have nothing to do with positive and negative charges, right? One is charges, one is north and south poles. But this is the first hint there's a connection. And this is the theme of the next couple of lectures. We'll see how, first of all, how they're connected, and also how we can make use of that, how we can create great machines, electrical devices out of that. Now there's a question of, okay, so now I know that they goes in concentric circles. So I need to assign a direction, right? Because magnetic fields are, we define that there should be a direction, but these don't go anywhere. There's no like north or south pole. So what's the deal here? Or what, like, how do we assign it? So what you can do is you just take a piece of permanent magnet and put it right next to here. Right, you can put something with a north and south pole like this. If you put it in the right direction, remember the north pole would try to follow the line. It's just like the positive charge in the electric field would try to follow the direction of the field lines. So if you place it in the right direction, it will stay there. If you place it in the wrong direction, it should flip itself around, and so that it follows the right way where the field lines would coincide. So it goes from north to south like this. All right. So that's how you can decide which way the field goes. All right. But after that, there's an easy way a mnemonic way to just remember this is called the right-hand rule. So in this chapter, you might see a lot of different right-hand rules or left-hand rules. It might get confusing. So I'll try to make this as easy to understand as possible and break that down. So this is, I'll call this right-hand rule number 1, okay? So how does it work is you try to just wrap your right hand around the wire and make sure your thumb is pointing in the direction of the current. Then your rest of your fingers basically will tell you, they will be indicating the right way of this. So this is just, it happens to be a nice convenient trick to remember. There's nothing fundamental to humans' right hands at all. It's a nice trick to, the right way to decide which way it's going is put a magnet here and see does it flip itself, and like which way does it flip along, and that's telling you which way is north and which way is south, or which orientation it's going around. But this is a nice quick trick. Without you putting a magnet there, you can immediately tell which way it's going. Okay, so this, I'll call this right-hand rule number 1. This you'll probably see 3 of these versions. Okay. So right-hand rule number 1. All right, so this gives you the direction of the B field due to a straight wire. And this is the most fundamental, I'll put the star on this side. This is the most fundamental starting point of it all, okay? So I've got the direction. How about the magnitude of the field? Okay, so you might expect the further away from the wire, the field would get stronger or weaker. What do you think, naively? The further away, the magnetic field would get weaker, right? Yeah, so that's right. And so that's not a trick question. So what is the magnitude? And I will tell you the formula basically without proof, because the proof is with not a law like the Gauss's law, called the Ampere's law, which is a little bit more advanced. So we'll defer that, but I'll just tell you the magnitude. So the magnitude of the B field due to a straight wire, right? So this is the source of the B field, is given by this, mu0 I over 2 pi r. Okay. So the 2 pi r is another interesting combination that appears. So I will label this I source, and I'll label this B due to a wire. Okay. Let's understand what every symbol means. So that's the B field, the magnetic field strength. Okay, so that gives you the magnitude, that gives you the direction. Okay, so just to make it clear, in case that's not clear, that means at this point, the magnetic field points this way. And maybe I should draw the field lines first. Let me draw the top-down view. So the top view of the wire, and we draw it like this. If the wire is going out of the page, we use a dot. If it's going into the page, we use a cross. The way to remember this is you can think of it like an arrow, like this. And if you look at it from the front, you see a dot, right? And if you look at it from the back, so if you have an arrow that is going into the page, what you see is the side of the arrow. So that's how I remember it. That's my way of remembering it. It's going into the page. And if you see a dot, it's like the arrow coming out of the page. You see this dot first before you see the fins. So that's going out of the page. So this is the convention. If you see dots, that means out of the page. If you see cross, that means into the page. And I always think of it as shooting like an arrow there. Right. So what are the field lines look like? They will look like concentric circles around it. That's not very concentric, but you get the point. And if this is out of the page, so I need to wrap my hand. So imagine the wire going right out of your screen right now. So you want to wrap your hand around it, but point your thumb the right way. So if this is the wire, you want to point your thumb out of the screen this way, not this way, right? So your rest of your fingers will tell you that this is the right way the magnetic fields are going. Let's use blue. I like blue better for magnetic fields, since B for blue. All right, so these are the magnetic fields. So how about the magnetic field vector? The magnetic field vector is tangent to the field, just like the electric fields, right? So at this point, this is the B field vector. At this point, again, it's a property of a location. So that's the B field. In fact, the closer I look at it, the longer my arrow should be, because the magnitude is stronger, right? The further away, if I have one over here, I should draw a very short arrow like this to represent it. As you can see, it's reflected over here. Everything here is a constant. So let's see if this makes sense. It means that what it's telling us, it's the magnetic field strength is proportional to the current and inversely proportional to the distance, which both should kind of make intuitive sense, right? The stronger the current, you'll probably get a stronger field, so that's not too hard to swallow. And the further away, the weaker it is. If you go to infinity, the field would go to 0, and there'll be no more effect like that. So Michael asked, would these be electromagnetic fields? I don't think that's a real word. There's electric field and magnetic field. So here we're talking about magnetic fields. If there's two at the same time at this location, I can put a positive charge next to it, right? And then it will have an E field and a B field at the same time at this point, at this location. Remember, it's a property of a location as well, just like electric field. Yeah, I guess then there's, I don't think people would call it, there's an electric field and a magnetic field. Maybe that's a better wording. Or if someone says electromagnetic field, that's what they mean. All right. Yeah, all right, so let me clarify. So yeah, so that's the current of the source, and that's the distance from the straight wire. And finally, this little symbol, mu naught, is called, it's a constant, just like the epsilon naught is for electricity, right? This mu naught, mu is the Greek letter for M. So it's spelled MU in English. So maybe that stands for magnet. I don't know. I'm making up reasons for it, but it sounds logical. It comes with a really annoying name called permeability of free space. And the value of it, you can look it up. It's 4 pi times 10 to the minus 7. It's actually a nice number. 4 pi times 10 to the minus 7, like that, with some SI units that I don't remember. So if I always work basically with pure basic SI units. So yeah, if you do that, you don't have to. I can figure it out actually. So if that is Tesla, 2 pi have no units, so it should be Tesla per amps, Tesla times meters per amps. So the units is Tesla meters per amps. But you don't have to care about this if you do it the right way, if you do it with SI base unit. So be careful. This is called the permittivity. I don't know who invented these stupid names, but free space. And don't worry, you won't get tested on what these are called. But just for teaching purpose, I'll tell you what they're called. So it doesn't do anything. It's basically like it's a unit conversion, because this guy is measured in amps, this guy is measured in meters, this guy is measured in Tesla. So in some sense, you need to. It's just some historical reasons we're calling something 1 Tesla, and then this guy needs a certain conversion rate. It's just like an exchange rate between countries. You have to convert one to another, but there's no significant meaning to that. The key physics is this. Okay? So the stronger the current, the stronger the field. The further away, the weaker the field. Okay? All right. So this is the primary source, let's call it, and now we can make something more complicated, just to torture you guys and or make life a little bit more interesting and able to make interesting applications out of it. Let's twist this in a loop and ask you, what does the electric field look like? Okay. Oh, but before I do that, maybe just for completeness, let me tell you, if it's going into the page, how would the field look like? If it's going into the page, then it's still concentric circles, but this time you're going to point your thumb using your right hand rule, right? Using the right hand rule, and point your thumb into the page. So try to point this into the screen right now, and can you see which way your fingers go? Should go this way. Right? So you can claim that the direction of the field lines, of the B lines, right, the magnetic field lines, are clockwise. And this one is going counterclockwise. All right, now let's try to twist the wire in a loop. Okay. So I'll twist the wire into a loop. So maybe there should be a battery over here, but let's not draw the battery. And just assume the current is going in a loop like this. Okay. Not the field, the current is actually going in a loop. Let me use a new page. A current loop. So this is called current loop. And so if I twist the wire like this so that the current goes around, how will the field look like? Well, use your basic knowledge of how does a straight line look and then try to combine everything together. So over here, they will look like this, right? So at this point, they will look like this. And if you use your thumb, I can't really draw in 3D, but if you use your thumb to point around the direction of the current, remember the rule is if this is the current, you want to try to point your thumb around and wrap your fingers around like this. Can't really draw a hand, you get the idea. So your thumb should indicate the current, and these would tell you the B field. Okay, so wrap your hand around there, you should see that the magnetic field will go around like this. So I will draw just a few over here. It should look like this. Maybe I'll just draw 2 lines per point. At this point, it will go around like this. Okay. And at this point, it will go around like this. Okay. And let me get the direction right. So it will go around like this. This. Okay. So you might want to try to connect all the lines together. It's a little bit hard to see, but hopefully you see that in the middle, inside the loop, the lines are all pointing up. Right? So inside the loop, can you see this one's particularly misleading. So let me redraw that. Okay. So point your thumb around it. That should tell you the answer there. So in the middle of it, you see that all the arrows are pointing out of the loop, going up, right? So you can kind of connect all them like this. In the middle, it's trying to do this. And on the outside of the ring of this loop, all of the arrows are wrapping downwards. So basically, I can try to connect it like this. Okay. So I'll do a better job by showing you a picture of it. So just how a straight wire would look. Just a few more examples, you can see that. Also, you can actually just draw a dot. If you're looking at a side view, you can imagine that. Okay, so if the field goes in and out like this, right? So at this point, it's going into the page. This side is going out of the page. But technically, it's wrapping all around like this. And it could go side. So now you can imagine if you're putting it sideways, then it's going like this, right? Or the other side. If you Google some of these, you'll have plenty of examples. You can check the direction with your fingers on your own, like that. This is the 2 scenarios where one is going into the page, one is going out of the page. And this is where the ring goes. Okay. So there's nothing new. Technically, it's the old current, it's the old right-hand rule like this. But when you put it in the ring, this is how it looks like. Right? Okay, so you can see that if I start connecting the lines, drawing a few more lines like this together, so this current is actually going the same way. Because the arrows is telling me it's going from north to south, you can almost imagine if I draw a bar in the middle, this almost looks like the magnetic field of a permanent magnet. Right? So remember, if I have north-south, remember this is how the permanent magnet field lines look like. Can you see the analogy like between here? So outside it's all going in, and inside it's almost like the loops are going up. Right? So inside this loop, the fields are going up, and outside the loop, the fields are going down. So it's almost look like a permanent magnet with a north pole here and a south pole here. So you can use the current loop to actually pretend or mimic the effect of a magnet. This is quite interesting. Yeah. Right, so yeah, there's plenty of pictures. You can Google it. So in reality, you need a battery to create a current. So you might, so in reality, this might have to be connected to a battery. But if you just focus on the loop part of it and don't focus on the other part, this is how it will look like. Right, so I think I have a redundant amount of pictures, which is completely not necessary. All right, so now that you know the direction, how about the field strength? Now the field strength, obviously this is not a straight line and it's more complicated. And you can see that it's not uniform, right? It's not like a concentric circle with a simple straight line like the previous slide. If Zoom would react to me, okay. Yeah, so like this is not as uniform, so it doesn't follow a nice formula. You see that's kind of like oval, ellipse kind of shape. It's not even like nice circles. So that's not easy to create a formula. There is one, but you don't need to learn it because it's complicated. You just need to learn the simple ones. However, we can use the current loop to make something simple, okay? How do we do that? Is by putting a lot of current loops next to each other, like this, okay? So if you take them and twist it with a lot, so you can almost imagine each of them is just basically a current loop, right? So if I zoom in over here, each line creates a little loop around it, right? So which way is my current going? Okay, my current is going up here. And try to wrap your right hand around with your thumb pointing in this direction. You can see that the around here, on this part, the current, the wire is coming out of the screen, right? So if this is going out of the screen, you put your thumb out of the screen, you see the arrows is not very clear, but it's pointing this way, right? So it's going around in counterclockwise. And by the time it goes here, the wire is now going into the screen, right? It loops in and it loops out and in again. So here, now it's going this way. It's going clockwise. So now put your thumb into the screen. So the rest of your fingers will tell you it goes this way. So now you can join up all the lines because basically the lines represents the magnetic field vector, and vectors add vectorially, right? So they add up and you can join up the lines. And if you have a very loose ring like this, then you get very wavy lines. But if you have a lot now, you'll get very nice uniform parallel lines like this. And this is called a solenoid. Okay, so so hopefully that makes sense, right? Inside it becomes very parallel, and outside if you just join them out, it should wrap completely around like this. So there's many pictures you can Google of a solenoid. Now a real solenoid will have the wires, let's say, going out of the page here and into the page here. So each of them will have the magnetic field this way. So if it goes out of the page, then this is the direction it's pointing. If it goes into the page, this is the direction it's pointing. So in the middle, they will basically, if you draw enough circles, they will all add up pointing this way. And outside, if you draw enough circles, you can connect these like this. And now this looks even more like a permanent magnet. So if you think back to the first slide when we draw a north and south magnet like this, right? So with a lot of rings, which we call a solenoid, you can basically mimic a lengthy bar magnet like this. So that's how you actually create a magnet from electricity. And this is the beginning of all the amazing applications we can do with electricity in our modern 21st century world that we live in. For example, if you want to pick up trash in a recycling facility where you want to recycle all the metal, metal are great at recycling because you can boil them and melt them and then recast them into different shapes. And it's a great recycling material. So if you have a pile of trash and you just want to pick up metals, then you can pass a huge magnet across. But the problem is if you take a huge permanent magnet, you suck up everything. And now you have a hard time. So you suck up all the metal from the pile of trash, you have a hard time pulling them out because the magnet is, if it's strong enough to suck them out of the trash, I doubt how many strong amount of horses you'll need to pull them away from the magnet. But with this idea, it's great because now you can pass a current through it, suck everything up, just turn off your switch with your pinky, and everything will just collapse because the magnetic field will disappear as long as the current disappears. Right? So this is called an electromagnet, and this is one of the first applications. You see why it is useful. Okay, so now I will also introduce the infinite solenoid. and see what the benefit of that is. If I have an infinite solenoid, so this lasts to infinity, basically all the fields are going to be constrained in the middle, and they cannot wrap outside. So you just get a nice uniform field in the middle of it, like this. Okay. And because if it goes to infinity, they can't really wrap outside. It's not really the complete reason, but it's a simple way to think about it without learning the proper Ampere's law. Right. So now you have very uniform field lines inside, and there is a formula for this. So for infinite solenoid, the B field inside infinite solenoid is given by mu naught Ni over L. Okay. So let's define each variable. Mu naught, you now know. Current is the current of the source. L is the length of the solenoid. And N is the number of turns, number of loops, or number of turns. Okay. So again, I being proportional, that makes sense. How about N? So the more loops you have, if I put in 10 loops, it will be, you have more magnetic field. So that makes sense as well, right? So what is less obvious is the length over here is, the longer it is, actually the weaker it would be. It sounds a little bit weird here, but let me introduce a new variable, because this is N per N over L. So I can call it a number density. So this is the number density, which is a number per unit length, number of loops per unit length, right? And I can rewrite this formula as B of infinite solenoid is mu naught little n I. So it's a little bit more compact. Okay. And you understand that this is the number density of it. So what it's really saying is, it's not how long it is, but it's how dense the loops are. Within 1 meter, if you have 10 loops, that is better than if 1 meter you only have 2 loops, for example, right? Within the same length, you want as much number of loops as possible per meter, per unit length, like that. Okay? So that should make sense, because if your loops are very spread out, then it doesn't really help this situation. So, right, so this formula gives you the magnetic field inside the, so it's this, tells you this B, the strength of this B. Now, in order to, so is there a quick way to decide which way the magnetic field goes? There is. Okay, so there's a quick way to decide instead of drawing all these little circles, because if I tell you, if I have a little loop like this, is there a quick way, instead of drawing all these little tiny loops, in order to decide which way the current, which way the B field goes? And there is, and this is another right-hand rule which you can use. So first, let's understand my 3D diagram first. What I mean is, on top, I'm going into the page. So let's say on top, I'm going into the page. And on the bottom, I'm going out of the page like this. Okay. So what you want to do is this time wrap your fingers around the current. Remember, before you were pointing your thumb on the current, but this time, if you have a lot of loops, try to wrap your fingers around the current. So you want your fingers to go into the page here and out of the page here. Okay. So what that means is, if you can see my camera, I don't know if it mirrors the screen in the right way, but you want your fingers to go, maybe you should try this on your own, to push into the screen that way and come out the other way. Now, can you see which way your thumb points? Your thumb is going to tell you what the magnetic field direction is inside the solenoid, okay? In fact, this is exactly the opposite of this case, right? So you can test it with this case as well, where you want to put your fingers, this time this side is coming out and this side is going into the screen, right? So you want the bottom to be going into, so the right way is you turn your hand around so that your fingers go into at the bottom and out of the screen from the top. Now your thumb should tell you that the B field goes this way. So this is not a fundamental rule, because this is basically coming from the first rule here, right? It's basically, oops, sorry, it's basically from this rule, but it's a nice trick you can use to determine. Go to the next place, please. Okay, yeah, to quickly determine the B field inside the solenoids. Okay. Let's see if I have other pictures. Okay. No. All right. That's it. Okay, good. So these are the, so a quick summary of sources is you can create them with permanent magnets, sources of B field. Okay. So learn how to draw the field lines for a permanent magnet like this and like this. So this one is just like this one is like this, with the red arrows going from north to south. And for a single straight wire, so if you have current like this, then these are the magnetic fields, and a single loop is, yeah, you can refer to the previous diagram, which is a little bit better drawn, okay, like this. So if I have a loop going here, for this guy, we do have an actual formula for it. It's mu naught I over 2 pi r. So the 2 pi r is quite easy to remember. If you have circles, you have some 2 pi r's there. And if you have an infinite solenoid, actually learn how to draw finite and infinite solenoids. If you have a finite solenoid, you'll get it to wrap around like this, which, as you can see now, if you just look at the outside, it looks like a permanent magnet. But if you look at the inside, if you have an infinite solenoid, usually infinite solenoids will just draw the top and bottom, and then you can draw the field lines inside. So for inside infinite solenoid, we have an actual formula for it. Okay, I'm not introducing any formulas for the single loop nor permanent magnets. I mean, yeah. These little bends over here is actually the edge effects for the finite solenoid, and for the infinite one, you don't have any edge effects anymore. They're all contained inside. All right. So now we answered the first question of what creates magnetic field, right? So the next question is, how do things react? So that's the second half of the subject, right? And now that we know what creates it, either permanent magnets or currents, right? The single loop and the finite loop is basically just a spin-off of this guy, of a single wire. Right? Okay, so this comes with the first experiment people did is this. They pass a wire through, they take a magnet and bend it into a U shape. So you have north and south on one side. So you have some, ignore the little edge effects. It's going to be pretty constant, most of it, if it's a large enough magnet. So you have a sort of almost uniform B field here, and you connect it to a wire, pass a current through it, connect to a battery, sorry, and pass a current through it. And suddenly they see, as soon as they turn the switch on or connect it to a battery, the wire suddenly gets pushed downwards, right? So imagine if you clamp both sides down, you can Google some YouTube videos of these experiments, clamp both sides down and the wire would suddenly get pushed down. It's not gravity. I mean, yes, gravity pushes down, but it's an extra force that the wire experience. In fact, if you pass the current through the other way, right? So you flip the current, go other way, you'll see it will actually, let's say you didn't clamp it too tightly, then you just clamp it loosely, then you'll see the wire just bend upwards, depending on how tightly you've done it. Or if you let go of the clamp, the whole thing will just pop out of the magnet, being pushed up. Right? So that's a second hint where the electricity and magnetism is again connected. They are not disconnected. So yeah, what's going on over here? People did a lot of experiments and try to figure out exactly what is the magnitude of this force. And so we call this a magnetic force, all right? So I'll give you the formula first. Okay, so this is wires in an external B field. Okay, so in this part of the subject, I won't worry too much about what's creating the external B field. It could be another wire. It could be really a source wire. It could be a source magnet. I don't care about the source. I'll care about the test object, which is the wire, and how it reacts to it. Okay, first of all, so we need to know two things: the direction of the force and the magnitude of this force, right? So this is, we say that the wire experiences a magnetic force. So let's tell you the magnitude first, because the direction is a bit tricky, all right? So the magnitude of this, although the direction seems more straightforward, it is a little bit more tricky. So the magnitude of the force on the wire by an external B field is ILB. Okay, the magnitude of it. So let's see if this makes sense. It's telling me the stronger the B field, the larger the force, right? That makes sense. The stronger the current, the larger the force. Also, it makes sense. And what is L is the length that is inside the B field, all right? So it's not really the length of the whole wire, because I don't care, even if it's a mile long, but most of it is not inside the magnet. That's not going to affect the force, right? It's the amount of length. It's only this little part, however long it is, that's experiencing the B force, the B field, sorry. So this should be pretty intuitive. So that's the current of the wire. That's the length. So this is the external. If you like, you can put a subscript external to remind yourself. And yeah, so this is the length of the wire in the B field. Okay, the second part is important. If you try to define this in a short question or something like that, make sure you say it's not the length of the wire. That's not true. It's the length of the wire that's inside the B field. And the other part is it's just the external B field that the wire is experiencing. That's it sitting on. All right, so that's pretty straightforward so far. How about the direction? How do I know which way is up and which way, if I pass the current this way and that way, how do I know which way is up? There's two ways to think about it. Okay, one way is actually people use the idea of cross products in math. So if you are familiar with cross products, then you'll be happy to know that the vector version of this is IL cross B. Okay, and now that I put a vector sign on it, I need to define the direction. What do I mean by the direction of L? Is the direction of this L vector is equals to the direction of the current. So for some historical reason, we don't put the vector sign on the I. We want to keep that as a scalar, and we want to keep the length actually as a vector. In some sense, you can treat these as one object if you like, I times L. But yeah, so the L is directly referring to the direction of the current. Okay, so in that first example where the B field is going this way, and my wire is going, let me draw the cross section of it. So I'm looking at it head on. Okay. So this is the north, this is the south, and I have a wire that is coming out of the page. So this is the current that's going out of the page. Okay. So let's use this idea of L cross B. So I is coming out, which means this L vector is coming out of the page, and the magnetic field is pointing this way. So the cross product between this to this is pointing up. So it will, the magnetic force, like the B force that the wire experience is up. Okay. So a quick recap on how to determine the direction of cross products is, if I give you two vectors, A and B like this, and ask you, they both lie on the page, first of all, and ask you what's the direction of C, what's the result of A cross B. So cross products will always produce a new vector that is perpendicular to both original vectors. Okay, so if I have A cross B, I will produce a new one, C, that either comes out or in the page. How do I determine whether it's in or out? Is you put your right hand along A and try to wrap your fingers towards B. Okay, so you try to put your, let me actually flip this around first so it's easier to visualize. Put your hand along A. Right. So put the base of your hand along A. So try to do that on your screen, and wrap your fingers in the direction towards B. So wrap your fingers to this way. Okay. And your thumb, if you point that up in a 90 degrees way, will tell you what's the result. B, sorry. Okay. So in this case, the result will be out of the page. So A cross B, the vector A cross B, or as I call it C, is going to point out of the page. Okay, so you can apply that scenario here is, I'm doing L cross B, right? So L is pointing out of the page because L is the direction of the current, and try to wrap your fingers towards the direction of the magnetic field, B. And you will see that your thumb is pointing on top of the screen this way. Okay. Now you can flip this around and notice A cross B is not the same, is not equal to B cross A. Because if you flip this around, try to put your base of your hand this time along B first and wrap it towards A. If I try to just slap my hand onto the screen like this, I can't really wrap clockwise to A, right? So I need to flip my hand this way. Remember, the answer is either in or out of the page because it has to be perpendicular to both of these. So the C vector is either in or out. So if my thumb is pointing out, there's no out of the screen, there's no way I can wrap my hand to the other side. But if I put my thumb into the page and point my hand along B, now I can naturally wrap my hand towards A. So the answer will be into the page like that. So the alternative scenario, if I have the B fields pointing this way, but my current now goes into the page, goes into the page, which way will the force go? Well, if the current goes into the page and the magnetic field is this way, this only, the result is either up or down, right? It has to be perpendicular to this, so it's either up or down. So you can try, first point your fingers, not your thumb, your fingers into the page because of I, but you can't really wrap your hands towards B if you keep your thumb pointing up. Now, let's try the other way around. If you keep your thumb pointing down and you have your fingers pointing into the page, now you can wrap your fingers towards the B direction. So L is pointing straight and B is pointing to the right-hand side like this. So in this case, the force, the magnetic force on the wire from the B field is down. Okay. So this is the third right-hand rule. You can, but let's call this the cross product right-hand rule. This is purely a mathematical right-hand rule. It's nothing to do with physics. Okay. This is just how you do. As you see, I can just use arbitrary A and B vectors like this. Okay. But there is a sneaky way, which is more tailored. Someone designed a nice mnemonic to remember it for the physics over here by the physicist Fleming, British physicist, called Fleming's left-hand rule. And he uses the left hand and assign a few mnemonics to make it very easy to remember. Fleming's left-hand rule. What you first do is learn this sign that if anyone takes 3B or heard of your friends taken 3B before, you'll see people keep doing this little sign. So what you want is have your thumb, first finger, and second finger, or index finger and middle finger, all in a mutually 90-degree way first, and then we'll put everything, assign 1 to each thing, okay, with your left hand. This is also what I call the 3D loser sign. You put it like this. So you have 3 L's at the same time. Anyway, so you how you assign what is, I'll try my best to draw this. Your first finger represents the field. Okay, so first our index finger, because F for field, so that's an easy way to remember. And then your second finger, or middle finger, represents current, because second, there's a C here. That's the only word that has a C between your thumb first and second finger, represents current, C for current, F for field. And don't question me too much, but your thumb, TH, sounds like force. All right, don't think about this too much, but that's the, so start with the first and your second finger, and then the last one is the force, to remember that. So let's try to implement it over here, right? So you want your first finger to point along the field. Okay, so the B field is, sorry about that B, it's a bit squashed, it's pointing to this way. So use your left hand's first finger or index finger, right, point around along the field. The second finger should go along the currents. In this case, it's coming out of my screen. Can you see your force, your thumb is pointing up. So this is another mnemonic. You can use this if you like, or you can use the cross product right-hand rule if you like. Either way will be fine. Let's test this one last time over here. So this guy, Fleming's one, is, as you can see, precisely designed as a mnemonic for this formula. But this is more general. It's a mathematic rule how you do cross products. Right? So for here, point your field, first finger around B, and the current this time you has to be into the field, into the screen, sorry, and you'll see the force is pointing down. Okay? Your thumb is pointing downwards. All right, so this is a very good arena to test for short answer questions, some potential spoiler alerts, to just give you this diagram and ask you which way the force is pointing. Right? So this is probably one important bit to master in this chapter. And finally, now that we know how wires react to B fields, remember wires are just positive charges moving through, right? If I have a current, it's just a positive charge moving through a wire. That means if I have an external B field like this, instead of putting a wire through it, I can actually just send a positive particle into the field and ask myself what happens to it, right? Does it exert an upward force or a downward force, right? So we can use the same idea with your, let's use Fleming's left-hand rule, is probably my favorite. Let's say you send a positive charge into, so send this into the page. Okay, so first point your left first finger along the field. Your current is, the current this time is the flow of positive charge, right? Goes into the field like this, and you'll see that this guy experiences a force downwards. Right. So if I attempt to draw a 3D diagram, which I might fail, but we'll see. if I attempt to draw a 3D diagram like this, and I send a positive charge careening into the field, as soon as it goes into the magnetic field, it will experience a force that bends it downwards, and it will shoot out the other way, other side kind of being bent downwards. Because in here, it's keep experiencing a force in this region, it's experiencing a force pushing it downwards. So you see the magnetic field does not only affect wires, because wires is basically made of moving positive charges, right? So also charged particles would react to, so here we have, the first page we have wires in an external B field, and in this case it's charged particles in an external B field. You can use the same Fleming's rule to find out what happens. Now, what if this is an electron? If this is a negative charge, remember negative charges just do the opposite of what positive charge do. So there's two ways to think about this. You can first think about what happens to a positive charge and then just conclude that the force on the negative charge is going to be the opposite. So this guy would get bent upwards. Like this. So this is the force on the negative. But if you don't want to first find the positive and then do the negative, just use the left-hand Fleming's left-hand rule. But this time, remember, if the negative charge is moving forward, make sure you know that this means this is basically the same as the current going backwards, because current is the flow of positive charge. So instead of pointing your, let's say if I replace this with a negative charge, then if the negative charge is going into the page, now substitute the word current as the opposite side, right? So if negative charge is going into the page, it means that if this is a current, it means the current is going out of the page. So put your second finger out of the page and your first finger in. So as you can see, this guy experiences a force that points up. All right, so you can test yourself with some exercise at home. What if I flip the field around? So if I have a B field this way, and I have a negative charge going into the page, which way does the force go? If it's going out of the page, which way does the force go? What if I send a positive charge into the page, which way does the force go? Up or down? Like that, or out, right? It's a quick way to immediately test this out. How about the magnitude? So here we have addressed the direction, and the magnitude you can deduce from the first formula where we had ILB, right? What is I? I is charge per unit time, essentially, but length per unit time is the velocity, right? So you can get this result. I'll put it in a box over here, QVB, like that. So that's the magnitude of it. And so this is the test charge that is moving, positive test charge. If it's negative, then it's the other way around. I mean, this is magnitude, so you always put in the positive value anyway. But the direction, make sure you determine it separately, right? There, unless you use the vector version, which I'll summarize in the next page. This is the velocity. This time it's not the current, right? It's the velocity of Q, and this is the external B field. You can put an external here, you can put a test here. Okay, and I'll give you the vector version as well, which is actually you just put vector signs everywhere. And so in vector form, you have Q, V cross B. It comes directly from the ILB version as well. So this is the test particle, this is the external field. Right, so you can contrast this with the electric field force formula, where remember for electric forces, you have this scenario, right? And this time, this is for the magnetic force experienced by the particle on Q by B external. This is the electric force on Q test by an external E field. Right? So if you have an external E field, you put a positive test charge here. This is the force it will experience. And this time here, if you have an external B field, if you have a charge over here, it depends on which way it's going. Notice that one interesting thing is if V is 0, it doesn't experience any force at all, right? If the velocity, if it doesn't move, it's only if it moves, it's only if it has a current, then it will have a force, right? And the direction is always going to be either perpendicular, it's always going to be perpendicular. Let's say this is going into or out of the page, then the force would be perpendicular to both its velocity, its direction, and the external B field. Okay. All right. I am running a little over and probably can't give you all the applications. Maybe I'll save it for Monday's lecture then. But let me go on for another 5 more minutes to address a subtlety over here so that I don't have to revisit on Monday. Okay. So here you want to make a note is, so far all the formulas we give you is if the V is perpendicular to the B. So these only apply if V is perpendicular to the B, or the current is perpendicular to the B field. The current, or the vector L, right, is perpendicular. So what that means is you see the B field here is going this way, and my particle is going into the page. What if it's not directly going into the page? What if the particle is also going this way? So what if they're parallel? What if they're at an angle? Then we need to be careful. Okay, so let's call it if the V is not perpendicular to B. Same thing with current. Okay. Now, first of all, is let's go back to the wire scenario. Remember when I put the wire directly, perpendicular to the B, it will experience a force. But if you do an experiment, I'm just quoting the result, is if you put the wire parallel to the B, so if the current goes this way and the magnetic field goes this way as well, then the net force on the wire is going to be 0. There won't be any force. So what about the in-between version? What about if let's draw the top view. Okay, so I'm looking from the top. Okay, so one scenario, the original scenario is if the B is going this way and the wire is going this way. The second scenario is if the B is going this way and the wire is also going this way, then the force is 0. This force is ILB, the magnitude. How about if it's in between? What if it's going at an angle like this? So now, this the rigorous way to think about this is you split this up into a part that is going perpendicular and a part that is going parallel to the field. So only the part that is perpendicular to the field, experiences a force. Okay, so there's an easy formula. Instead of trying to resolve the vector for it, for those who don't like resolving vectors, this might be good news for you, is all you need is this angle. It's called the included angle. So the angle that is included between the B vector and the L vector, or the velocity vector, depending whether it's a charge or a wire. And the answer is ILB, and you put at the end a sine theta included angle over there. I don't really need the brackets, like this. In some sense, this is the more general formula for all the 3 cases, because if theta is 0 degrees, that means they're parallel. So sine theta is going to be 0, right? So the force is going to be 0. So this one formula here, I'll put a star next to it, encapsulates all 3 cases. If theta is 90 degrees, then sine 90 degrees is 1. So the force, the magnitude, is ILB, which is the first case. And if theta is somewhere in between, then you have the in-between case. This is basically someone who did the job of resolving the vectors for you and then got this formula here. So it nicely encapsulates all the first few cases. So same thing if it is a charge. So if it's not a wire, if it's a charge, right? So let me copy this. So replace that wire with a moving positive charge. So this time, this is a positive moving charge. And this is the velocity vector of it. Then you have the similar case where this time, so here, the magnitude of the force it's feeling is this, the magnitude is 0, the general case is QVB, and just put in sine of the included angle in there. But if you know how to do currents, you know how to do if you know how to do it for the currents version, you know how to do it for the positive charge version, because current is just the motion of positive charge, if you understand that. Okay, all right, so next time I'll show you how do we construct a motor out of this, basically how to make electric motors. Although Tesla has nothing to do with electric cars at the moment, you'll see that is actually, this is actually the theory that electric cars are based on. So that's actually a good company name. So we've talked about gas-propelled cars, we'll talk about electric cars in next time, and also connect that with more magnetisms, electromagnetisms, pulling the two together. All right, okay, any questions? Okay, if not, I'll end here. So yeah, I think the main thing to practice out of this is practice the directions of the, if I give you a B and I find out which way the force is. And it doesn't, the V also, it doesn't also have to be, actually here, this is a pretty good example. I'll put it in a box as well. Try to find out which way the force goes for these two cases on the wire. So question, find the direction of the magnetic force it results. So a quick tip is, if the wire is pointing this way and the B field is pointing this way, you know the force, the resultant force has to be perpendicular to both, right? Because of the cross product, it's L cross B in the vector version. So it has to, the force has to be either in or out. So you just need to answer, is it into the page or out of the page? Right? And same thing over here. You can fill in the rest of the blanks yourself. Okay. All right, good. Thank you very much. And have a nice weekend. I'll see you guys next week.